Hi, so this summer I've been working on a launcher prototype for inertial transfer, which would support in-space assembly. My mentors are Danette Allen and Jim Ecker. So a little bit about me. My name's Jamie O'Brien. I'm from Bethlehem, Pennsylvania. I'm a rising junior at Olin College of Engineering, studying computer and electrical engineering. So inertial transfer would support in-space assembly if they need to transfer some payload a really long distance through space. Currently, we would have to tether it and move it very slowly, but ideally if we had two agents with some payload or package, and the launching agent would transfer the package to the receiving agent, it would be much faster and more efficient. So this summer we wanted to model this in 2 dimensions. So the launching agent on our air-bearing table launches the puck to the receiving agent, which is our UR3 arm, which you can see behind me. And then they also need to communicate, very important. So the launching agent sends its plan to the receiving agent, and the receiving agent executes its own plan accordingly. So this summer I designed and built a prototype for a launcher, and I've also been working on some basic communications between the launcher and the receiver. Basically, I needed to design a launcher that is given a desired velocity and angle, and then launches the payload toward the receiving agent and communicates what it needs to, whether it be angle, velocity, bearing, expected intercept. Our receiving agent is the UR3 arm, and I decided to make a spring-loaded launcher that has an electromagnetic trigger and Arduino to ROS communication capabilities. Of our design requirements that we decided on at the beginning of the summer, we needed to impart a set velocity. We decided about 0.5 meters per second would be our maximum velocity that we'd want to go, because we want to give the UR arm time to plan and execute before the puck makes it across the table. We also need to report the velocity, so I made an infrared photogate time of flight sensor to report the velocity. It needs to fire at a set angle, so we wanted a mechanical range of plus minus 90 degrees, and it needed to report the bearing coming from the Arduino. We wanted it to be repeatable. We were hoping for 5 launches with consistent velocity, angle, and we want it to be hand portable so that for testing we can reconfigure things quickly and efficiently. So one of my first ideas was to make it kind of like a pinball launcher. So I was going to use a spring and have it pulled back, and it was an entirely mechanical design, but I wanted to automate it more and make it more robotic in some way. So I decided to use the linear actuator over here with an electromagnet on the end. So what happens is the linear actuator extends and meets, there's a piece of metal on the back of this puck carriage here, and when it extends, it turns on the electromagnet and then pulls back. And so when it pulls back towards that wall, this spring compresses, and then when it gets back far enough, it turns off the electromagnet, and then it releases and launches the puck. Here, there's a little tab on the carriage to keep the puck from floating away before it's launched, but there's this structure to deflect the tab so that the puck can leave the carriage. And over here I have the IR LED and receiver, so we can get some velocity reading. So originally I was going to hold the puck in place using the launcher structure itself, not the carriage on its own. I was going to use springs and tabs that rotate. And then I thought maybe I could do it with some soft material, so have the opening of the launcher be wider, so then when you pull it back into the narrower part, it closes around the puck, and then when it goes out, it releases the puck. But then I ended up deciding on what I just mentioned, the tab that deflects up and releases the puck. And then I wanted to be able to reconfigure the angle easily, so originally I was going to have some mechanical jig, either discrete with grooves that you can slide the launcher into, or one groove that you can use a set screw and turn and have a more continuous angle option. I ended up using a servo to give us a more continuous range, and it's measurable because we can take whatever we set it with the microprocessor and report that to the receiving agent. So when the puck breaks the IR beam from the LED to the sensor, it starts recording the time, and then as soon as it receives the beam again, it calculates the velocity of the puck using the diameter of the puck and the elapsed time. This is my launcher overall. You can see it on the table there. There is an Arduino in this top box with it has a motor shield on it to handle the electromagnet without any kickback. There's the servo in the back, which you saw on the jig before, and this front part is what I showed in one of the earlier slides. So this is what I built. That's what it looks like. So right now we have it, you can see it in this video, but we have the arm moving to meet the puck where it's going to go. So the launcher decides what angle it's going to use and how fast it's going to send it, and then it reports that to the receiving agent, and the arm moves accordingly to catch the puck or intercept it. So overall, we can impart a set velocity. We've consistently been getting about 0.32 meters per second, which is within our range and slow enough for the arm to react to. And we have been able to report it using the IR photo gate, and the fire at set angle is possible because of the servo I'm using, but because of the way I printed the jig, right now we don't have the full 90 degrees, but that's a really simple reprint fix to expand that to the full 90 degrees. We can report the bearing using the Arduino and how it sets the servo. It's repeatable. We got 30 launches with consistent velocities and bearings, so that far exceeded our expectation of 5, and it is hand portable. It's around 40 centimeters long. It's really easy to pick up. So to validate the IR, we use the Vicon system, and I made that little test jig, and we took 60 samples, and the error was about 0 to the 2 millimeters, and the standard deviation was about 2 centimeters per second, and the testing velocities were around 1 meter per second. These are some of the passes from that IR testing. As you can see, the red line is the IR calculated velocity, and the blue is from the Vicon system. The blue captures more of the negative acceleration as it drags across the table, but you can see that it is in the right ballpark most of the time. And that is all 60 passes that we did when we were testing the IR system. It was following Vicon pretty closely. We measured the IR measurements while launching it from the actual launcher, and we did 30 samples, like I said, with the same desired angle and velocity. Our mean velocity was about 0.32 meters per second, and the standard deviation was about 1.78 centimeters per second, which is within the standard deviation that we calculated using Vicon, so it's consistent with what we saw before. So for communications, right now we have a user giving the desired velocity and angle to the launcher through serial input, and then that sends a serial message with the measured velocity and angle to Ross, and Ross takes that and calculates the anticipated intercept coordinates and gives that to the receiver, and the receiver comes up with a plan and executes the plan to intercept the puck. So that's what we're doing right now. In the future, with inertial transfer and in-space assembly, this communication plan would change. Likely there would not be a user in control all the time, so there would need to be more autonomy in the system. So those agents would need to be fully autonomous. We'd need an autonomous decision-making system. I don't know if we would be using ROS or not. That could likely change. Some server that the robots can communicate on, and some human-run monitoring system, likely. So in the future, we can machine parts out of higher fidelity materials. Most of it is 3D printed as of right now. for rapid prototyping. We could also use more accurate sensors to get more precise velocity measurements. Currently, the IR receiver that we're using is a hobby level, $5 sensor. We can also remake the jig to reach a wider range of angles. Like I said, we just need to move the mount for the servo back and it'll increase the range. And we can implement more communication, so we would want the communication to be more two ways. Right now we have the launcher sending a plan to the receiver and that's about it, but we could say, like, can I launch this to you? I have launched the object towards you. Do you see it? I have received the object. So more in-depth communications in that way. We could consider communication security, like are our robots only communicating with our robots? Is anything intercepting these messages? And adjustable springs and magnets to achieve launch at desired velocity. Right now, we can adjust the amount of deflection to some degree, but if we wanted to largely change the velocity, we would need to switch out the springs manually. Are there any questions? So currently the part of the jig that holds the servo gets in the way of the part that rotates and keeps it from moving the full 90 degrees, so we would just need to change how that's mounted and then it would open up the... Well, when I got it working, originally it was moving pretty slowly, so I figured I'd add a stronger spring to make it move faster, and then it launched a lot faster than I expected to, and it actually broke part of itself and I had to reprint part of it. So I would definitely do more analysis before just changing out parts in the future. I probably won't make that mistake again.